Hi students, in this video let us review the concept of polynomials that we studied in week 6. So in week 6 what we have studied is we have defined the polynomial in an appropriate way. In particular, what I have done is I have given you one layman's perspective about the polynomial, and one is mathematician's perspective. So in this case, if you notice the finer difference between mathematician's perspective and layman's perspective is a layman can generally say a polynomial even if it is with rational powers, rational exponents, and a mathematician will not consider that polynomial as a polynomial. The difference comes essentially because the way we are using the domain of definition. For example, when we are talking about a layman, he may not have a clear understanding of the domain of definition. So therefore he is talking about something which is very vague. But a mathematician clearly understands the domain of the definition. Therefore he will say that something is not a polynomial if it is not defined. The function that we are defining is not defined over a real line or some part of real line. So when I am talking about a polynomial, I am always assuming, or a mathematician is always assuming, that the function goes from R to R. So in that case, when we talked about the definition of functions, the definition of polynomials, the mathematician will call this x cube plus x square plus x plus 1 as a polynomial. This is, let us say, this is fx. But he will not call f of t equal to t raised to 1 by 4 plus t plus 4 as a polynomial. Why he will not call? Because when I take the fourth root of a negative number, or to simplify the matter, let us take the half, t raised to half. So when I take a square root of a negative number, this actually violates the definition of a function over here. It is not defined on R. Then I have to restrict the domain to the interval 0 to infinity. Therefore, I will refrain from calling this function as a polynomial, though it is a polynomial in the interval 0 to infinity. Right? That is where I want you to be clear why we introduced the two perspectives in the definition, layman and mathematician's perspective. Sometimes engineers also make this mistake of considering layman's perspective of a polynomial as mathematician's perspective. So it's just a note of caution that you should be aware of. So in particular, what is a polynomial? So as I mentioned in the introductory video, poly means many, and poly means many, and nomials, so neoms, that the plural is names or constituents or terms, to be precise. So all these neoms, so these are some Greek and Latin words, and therefore they are used here, and these are terms. So a function involving many terms, and then we are actually talking about what kind of terms these functions should have. Then we say that it should be, if I am talking about function of x, then it should be integer coefficients, not integer coefficients, 1 minute, let me rewrite it. Fx should comprise of, fx, a function, should comprise of many terms. So many also includes 1. And what are the forms of these terms? The forms of these terms should be either they are with real coefficients. I assume that you are clear with the notion of polynomial. So I am just briefly summarizing. All the coefficients should be real, otherwise we cannot deal with functions from R to R. Second thing is the variable or variables, whatever you choose. If it is a polynomial in one variable, it is single variable, should be raised to natural exponents. Now natural is something that you have to be very careful. So what is a natural exponent here? I am talking about the natural exponent in the context we defined in week 1. So it includes 0. To be clear about this, you can also say this natural within quotes and say natural is equal to whole numbers or non-negative integers. So it should be very clear in your mind. If the polynomial or if the expression is of the form f of t is equal to t raised to minus 1 plus t plus 1, this is not a polynomial. This is not going to be a polynomial. So that should be clear in your mind. Okay, fine. So this is about the basic introduction to our definition of polynomials. So what are the key points? First, polynomial should always be defined from R to R. Therefore, we have two perspectives. One is layman's perspective, one is mathematician's perspective. Mathematician's perspective says that a polynomial should always be defined from the domain which is set of real numbers. A layman's perspective may be a subset of real numbers. The domain may be a subset of real numbers. Both can be used indistinguishably when you are considering an engineering problem. But at the back of mind, this should be clear that you have to use a mathematician's perspective in order to understand the problem precisely. Now, the name polynomial comes from the two words poly and neoms. So poly means many, neoms means many terms, and the expression having many terms with real coefficients and variables having natural exponents is called polynomial. Okay, so we have identified what is a polynomial. Now let us try to do some algebra with these polynomials. Let's try to do some algebra with these polynomials. So what kind of algebra you can do with these polynomials? First one is addition. So let us see how we can add two polynomials. So based on our characterization, let us try to see how we can add the polynomials, and then we will go further. So for example, because it's a function fx, so I can write this polynomial as px, and px, if it is a polynomial in one variable, which we are focusing currently in this week, it will be given as an x raised to n, an minus 1 x raised to n minus 1, and so on up to a1x plus a0. A0 is a constant term, so it is essentially x raised to 0, and qx is another polynomial which is given by bm x raised to m, bm minus 1 x raised to m minus 1, and so on b1x plus b0. Now you will see the clear-cut distinction between these two polynomials. One is raised to the power n, another one is raised to the power m. And the way we have written the polynomial in a descending order of powers or exponents, you can easily visualize that n is the highest order exponent in this particular expression, which is given by px. In a similar manner, when you observe qx, m is the highest order exponent when you are given qx. So these terms will be called degree of the polynomial. Okay, so what is the degree of the polynomial px? Degree of the polynomial px is n, and degree of polynomial qx is m. As these two are positive integers or non-negative integers, even if it's a constant polynomial, there must be an order relation between these two. So without loss of generality or for sake of computation, assume n is less than m. In that case, the question is, how will you add these two polynomials? So in order to add these polynomials, because I have assumed n to be less than m, I know that the degree m is higher. So what I will do in this case is I will rewrite px in a form which is of the form am x raised to m plus am minus 1 x raised to m minus 1 and so on. Somewhere along the line my an will match, and that will be an x raised to n, and so on. The same polynomial continues till a naught, and then I will write qx. Then what I will do is I will write the coefficients of the polynomial qx just below this polynomial, which will help me in adding the two terms. So this will continue, it will be bn x raised to n plus so on up to b naught. Now the polynomial will look, the addition of two polynomials will look more or less decent. So I just need to add these two terms. That means I need to add this term with this term. Now you have to give weightage to the terms associated with this. That means the coefficient of x raised to m should be added to the coefficient of x raised to m, and therefore my resultant polynomial as it stands will be very simply written as, let us say I will write it here, px plus qx equal to, so just take the terms containing x raised to m, sum them together, am plus bm x raised to m, am minus 1 plus bm minus 1 x raised to m minus 1 and so on up to a naught plus b naught. Okay, so one finer things, because I have written this polynomial, what are the values of am minus 1 and up to an plus 1? All these values are 0. So in these cases the terms which are here will essentially chop off. That means these terms will vanish up to an plus 1, and you will simply get this. Let us do one example in order to clear our understanding and write it as a general formulation. So let me just create some space. Okay, so use this formulation and write it as a general formulation and treat it with example. So if I have polynomial px which is given by summation over j is equal to 0 to n aj x raised to j, and I have asked to, and I have been given a polynomial qx which is summation over k equal to 1 to m, or not 1, 0 to m bk x raised to k. Remember j and k are dummy indices, and therefore I can, if this is the case, then I know the answer that if n is less than m, whatever answer I have given, if n is greater than m, you will have to go up to n. So I can write px plus qx to be equal to summation over, it doesn't matter whether n is less than m or n is greater than m, j is equal to 0 to maximum of n and m, whatever is the maximum I will go up to that. I will replace the values which are not there with the value 0, and therefore I can simply write this as aj plus bj x raised to j. Okay, so it is that simple. So how it translates in our example? Very simple. We will use a simple example of px being equal to x square plus 1 and qx is equal to, let us say, x cube. What is px plus qx? Use this formulation, there are no terms which are clashing with each other, aj plus bj. So all these things will remain intact and I will get x cube plus x square plus 1. This is the answer. So we have already actually done addition. Then a minor thing in difference is nothing but you are talking about px minus qx. So if I want to subtract these two polynomials, what will happen? Minus x cube plus x square plus 1. This is the difference. Now if I want to formally write the definition of a difference or if then I can simply copy this, substitute, I can simply copy this and substitute px minus qx. This is again summation over j equal to 0 to maximum of n and m aj minus bj x raised to j. That's all. So this is the formula for difference. These are very simple formulations. The main trick comes when you are using multiplication and division. So let me focus on multiplication first and then we will go on and do the division. So I have been given a polynomial of the form px which is equal to summation over j equal to 0 to m aj x raised to j. Let us put this as n because earlier I was using it as n. So let me write it as n only. And the other polynomial is qx which is summation over k equal to 0 to m bm. Not bm, bk x raised to k. Okay, so these are the two polynomials. Now I want to find what is a product of these two polynomials. How will I write a product? It is px into qx is the product of two polynomials and I want to write it. So what essentially we are doing is we are first writing px which is summation over j equal to 0 to n aj x raised to j and then multiplying this with the term by multiplying this term by term with bm x raised to m plus so on up to b naught. So this entire summation is multiplied with each of the terms and then we will rearrange the terms, and when we rearrange the terms you will get the coefficients of the form x raised to j plus m, x raised to j plus m minus 1. So we will club them all together and once we club them all together I will get j is equal to 0 to n plus m. Then I will get this thing to be equal to k is equal to 0 to j. I will get a k and b j minus k, this entire thing raised to x raised to j. This I have derived explicitly in our videos. So you just look at those things and then you verify the result for yourself. Now let us come to the division part. It is actually a long division that we are trying to figure out. So given a polynomial, let us say the polynomial is px which is summation over j equal to 0 to n aj x raised to j and qx is again summation over j is equal to k is equal to 0 to m bk x raised to k. What we are essentially trying here is I want to divide a polynomial. So if I want to divide a polynomial I need to know the order relation between this particular point and this particular point, whether n is greater than m or n is less than m. If n is greater than m, the division of px by qx is possible. If n is not greater than m or n is equal to m, that still I can do some division kind of thing. But if n is strictly less than m, then px by qx is not possible. So for n less than m, px by qx I cannot actually divide. This will lead to some rational function which we are not studying right now. but this will lead to some rational function, so there is no question of division. When n is greater than or equal to m, this px by qx makes sense for us, and we will try to divide it. Okay, so what we will do when we try to divide this function, we have already seen through several examples how to divide a polynomial. So in particular, we will establish one algorithm. So what we will do in that algorithm is, that means I am talking about n greater than or equal to m. So when I consider the algorithm, I will consider the leading term, that is an x raised to n, and I will consider the leading term of the polynomial qx, which is bm x raised to m, right? And this together will give me an upon bm x raised to n minus m. So what I will do is, I will go ahead and multiply this bm x raised to n minus 1 with the term which is px by qx, so which is, I will multiply it with qx. So this will give me some term. That term I will use and I will subtract it from the term px. So I will essentially, what I will do is, I will write this simply as, in the nomenclature wise, px, this is qx, divisor, dividend, you can, then I will first take the term an upon bm x raised to n minus m. Then I will write a term which is which is actually px as it is, and I will write a term which will actually subtract an by bm x raised to n minus m into qx. Then I will look at the remainder term, the terms that are remaining. Let me call that remainder term as some p1x. Again I will analyze this p1x, whatever is the term remaining, so this p1x. Then I will take the leading term of p1x. So this is algorithmically, take the leading term of p1x. Let us say that term is some aj x raised to j, and I will check whether it is this j, the leading term, this exponent, is less than, the degree of this is less than this term, less than the degree of qx. If so, then I will stop here. If not, I will continue and I will take this term aj and I will simply add the term aj upon bm x raised to j minus m, and then I will go ahead and compute that particular term aj upon bm x raised to j minus m with the term qx, and then again I will subtract this term, and then I will find some another polynomial p2x, and so on. This process will continue as long as the terms that are yielded in p2x or pjx are of lesser degree than the degree of qx. This is in short the summary of the division algorithm. Let us demonstrate it through simple example. Let us take the example x square plus 4x plus 4 and divide this polynomial with x plus 2. Okay, so in this case, what is our you just see this, the px is x square plus 4, x square plus 4x plus 4, qx is x plus 2, and I am dividing it. So what I will do is, I will take this, what is an here, it's a2, so which is 1, and this one bm is 1, so this simply gives me x, and this simply gives me x, and then I will have x square over here. Then if I multiply it with that, then I will get x square plus 2x, and this essentially gives me, so 4x minus 2x will give me 2x plus 4, and then you simply do here, it's 2, that is that is the p1x is 2x plus 4. It is not of lesser degree, so I will simply use one more thing, so I will use 2, and then I will get 2x plus 4 as it is, and then minus minus, I got, fortunately I got 0. If I had used some other number instead of 4, I would have used 8, then I would have got some constant. That's all. This is how we will do a division of a polynomial. That's all we studied in week 6 essentially.